Class, welcome to the next chapter, chapter 12. In chapter 12, we will be talking about polar coordinates and parametric coordinates, mostly polar coordinates and conic sections, and how that relates to calculus. So for this first section, we're going to talk about parametric curves. So a parametric curve is basically just a function that is modeled by using other functions. Okay, so parametric equation is an equation whose variables have been parameterized, meaning that the variables of the function are functions of a different variable themselves, right? So generally we talk about time when we do this. So defined in terms of a function and another variable called parametric equations, right? So x is it given by a function, a parametric equation. Y is given by another function, which is a parametric function, parametric equation. So these two functions together can act like a single function. Okay. So once you parameterize a function, it is now called a parametric curve. Okay. A parametric curve is different than a normal curve because it has a direction in which it travels. So we're really just going to do one example. It's a very, very short section. And then in the next section, we'll talk about how to do calculus on these kinds of objects. Okay. So for example, let's sketch and identify the curve that is defined by x equals t squared minus 2t and y equals to t plus 1. Okay. So x changes over time and y changes over time, just like in a regular function. So x is defined by a function of time and y is defined by a function of time as well. So what we're going to do is we're going to look at what happens as time moves on. So we'll plug in different values of t, get a table, and we'll just start to plot those points on a graph. Okay, so here we're moving rather slowly. So we'll start off with t equals 0, okay, or -2, I guess in this case. And so if I plug in -2 to both equations, I'll get out an x and a y, and then I can write that as an ordered pair so that I can plot that point. So for x, I'm going to get 4 plus 4, okay. For y, I will get -2 plus 1 or -1. So the ordered pair at time t equals -2 is 8, -1. For -1, I have 1 minus 2, so I'm sorry, plus 2, so that's 3. Here I have -1 plus 1, so that's 0. Okay, so 3, 0 is the next one. Here, if I plug in 0, I get 0. Here I get out 1. When I plug in 1, I have 1 minus 2. And here I have 1 plus 1. And when I plug in 2, I have 4 um, minus 4, so that's 0. Here I have 3. Okay. Plug in 3, I have 9 minus 6 is 3. Here I have 4. Okay. And then for 4, I have 16 minus 8, so 8. And this is 5. Okay. So I have a nice set of points here. And I'm going to go ahead and plot these points in order. Okay. In order as time progresses. So the first one is at 8, -1. Okay. The next one, so that's at t equals -2. The next one was 3, 0. So that was t equals -1. So as you can see, we're moving in this direction. Okay. Next, I have 0, 1. Okay, that's at t equals 0. At t equals 1, I have -1 and 2. And then I have 0 and 3 for t equals 2. Okay. 3, 4 for t equals 3. And 8 and 5 for t equals 4. Okay. And then I continue to move in this direction. So as you see, it is a parabola that has been rotated um, along the x-axis. Okay. Centered along the x-axis. So the equation for this parametric equation is x equals y minus 1 times y minus 3, right? My function is an x here, and I have zeros at +1 and +3. So this is a parabola that would look like this, okay? Right? Because I move over 1, up 1, over 1, up 1. So that means that this is not multiplied by any scalar amount. So it's very clear to me that my function of x and y has these as 0, so this is this factored form. Okay, so even though my function has been parameterized and I have the parametric equations for this um, function, I can actually use this x and y to find my equation. Right? The same equation that I have here in the standard form, I can take the paramet paramet oh man, parametrization that I have been given, and I should be able to mess around with it and come up with what I have here. The way that I do that is I take my either my x or my y and I plug one into the other. Basically, I'm solving it like a system of equations. Okay, so I basically just solve for t and then plug one into the other, and then there we go. That's how I'll get my function out. Okay, and I simplify what I have. So, okay, x is t squared minus 2t, y equals t plus 1. The easiest t to isolate is going to be this one, right? I just subtract 1 on both sides. So t is y minus 1. So everywhere I see t, I just replace it with y minus 1. Okay, that's the easiest one because this x is very convoluted. I can't isolate t here. It's obviously much easier to use this one. Okay, so when I see t squared, I replace it with y minus 1 squared minus 2t, so minus 2 y minus 1. And I just simplify. Okay, I just simplify my equation. So here I need to expand this out because y minus 2 or y minus 1 squared. This negative 2 I'll distribute across. So I'll just multiply everything out. Combine my like terms. So this is a negative 4y and this is a 3. And then if I go ahead and factor that, look at that. Isn't that amazing? I got the exact same parametric equation, the exact same equation in standard form. Okay. There are a few common um, parametrizations. One is x equals cosine of t and sine t. You've seen this in trig, right? This is just a circle, okay? For 0 to 2 pi. Okay? That's going to give the unit circle. If I multiply by a value of r here, then I get a circle of radius r, okay? Notice that if I square x and I square y and I add them together, I get cosine squared plus sine squared, which is equal to 1, which is x squared plus y squared equals 1, the unit circle, okay? If I multiply cosine times r and sine times r, then it's a circle of radius r. Okay, and again, this is from 0 to 2 pi for my time. And we know which direction it goes, right? Now, if I have different scalar multiples of cosine and sine, then either the x direction is going to be elongated or squished, or the y direction is going to be elongated and squished, and I'm going to have an ellipse. Okay. The interval for t in the previous example is it determines how many times we go around the circle or the ellipse. So for instance, if I went 0 to 4 pi, I would just go around the circle twice. Okay. So my interval for the domain of t is important as well. Let's say x is a times t plus x naught, so some sort of a line, and y is another linear type of function, b times t plus y naught. This is going to give a line. So if both of these look like a line, it's going to be a line that goes through the point x naught and y naught, and it's going to have a slope of the ratio of b over a. Okay? Change in y over change in x. Parametric equations are very useful in describing the path of a particle through space over time. So if you think about a piece of dust floating, you know, through the air, that is something that you would model with a parametric equation. Okay, and that's it. Very short video. So good start to chapter 12. The videos will get longer as we progress. So I'll see you guys on the next video.